Part 3 of Unit 14 is about Gibbs free energy and the third law of thermodynamics. The third law of thermodynamics says that the entropy of a pure crystalline substance at absolute zero is zero. So just a reminder, absolute zero is 0 Kelvin, and that's the only possible temperature at which there is only one single microstate. That's the least possible amount of entropy in the universe. It's the lowest possible energy state at the lowest temperature. That's our reference for determining entropy for other substances at different conditions. Let's talk a little bit more about entropy. Here's a table of standard entropies, and these can be used to find delta S, the entropy change for a reaction. You can see that as the molecules get larger and more complex, they're going to have greater entropy values. That's because there's more bonds and more atoms, so that's going to result in more movement and more possible microstates for each of those molecules. These values are used just like delta HF values to find the standard entropy change, the products minus reactants equation. One note about these, you see the little knot symbol at the top right of the S. That means standard conditions. That's 1 mole of these gases or 1 molar solutions, and the pressure is 1 atmosphere. The entropy values might change a little bit if we're not at standard conditions, but typically you're going to be dealing with S at standard conditions, 1 atmosphere pressure, and 1 mole of gases. So to use those standard entropies to find delta S for a reaction, delta S is equal to the sum of the entropy change for the products minus the sum of the standard entropies of the reactants. Just like delta HF values, products minus reactants, when you are doing these, you need to pay attention to the units given. Enthalpy of formation was given in kilojoules. The units on the standard entropy table are typically joules per mole times Kelvin. Let's talk about a new quantity called Gibbs free energy. It's a quantity that combines enthalpy and entropy into one term. It measures the useful work that's obtainable from a system, and it helps decide the spontaneity of a system and help us relate equilibrium to entropy. Gibbs free energy is a symbol G, and our basic equation for finding Gibbs free energy is delta G is equal to delta H minus T delta S. Or if it was for finding delta G at standard conditions, it would be delta G standard is equal to delta H standard minus T delta S standard. A couple notes about this equation. Your temperature has to be in Kelvin. And like I said on the last page, the units that are given for delta H and delta S are different. This is usually given in kilojoules. This is usually given in joules. You need to make sure that these are in a consistent unit so that you don't accidentally mess your answer up by 3 decimal places. Some notes about Gibbs free energy. If delta G is negative, that means the forward reaction is spontaneous. So if you're trying to figure out if a reaction is spontaneous and you know what delta H and delta S are, you plug them into that equation. If delta G is negative, that reaction in the forward direction is spontaneous. If delta G is 0, that means the system is at equilibrium and that it's spontaneous in both directions. And if delta G is positive, that means the reaction is spontaneous in the reverse direction, or that it's not spontaneous the way that it's written in the forward direction. This is a table that's relating free energy and temperature and enthalpy and entropy. There are usually a couple multiple choice questions on the AP test per year that come off of this table, relating the different possible signs of delta H, delta S, and then delta G. This term here, the minus T delta S, sometimes that's summarized as the entropy term because it it combines temperature and the change in entropy. But it's not a bad idea to memorize this table. If you can't memorize the table, this can all be derived by plugging some experimental or test values into the Gibbs free energy equation, but it's just easier to kind of remember the four details here on the right side. Similar to standard enthalpy and entropy, standard free energy can be calculated using a table of standard values from this equation. Delta G standard is equal to the sum delta G standard for the products minus the sum of delta G standard for the reactants. So delta H, delta S, and delta G can all be found by using the products minus reactants equation, as long as you remember to pay attention to the coefficients in the balanced equation. We can also use free energy to relate it to equilibrium. So under non-standard conditions, so not that we don't have that little knot symbol, we're not at 1 atmosphere pressure or 1 mole of gas or 1 molar concentration, the free energy change can be found this way. Delta G, so our non-standard delta G, is equal to delta G standard plus RT times the natural log of Q. In this case, R is equal to 8.31 joules over mole times Kelvin, because that's our value of R that has the joule term, not volume in it. We're looking for the one with the energy term, not volume here. Temperature has to be in Kelvin. And Q is your reaction quotient, which we used back in Unit 11 in equilibrium, the products over reactants equilibrium expression. It's just not necessarily at equilibrium. So that's how we can relate the reaction quotient and equilibrium concepts to delta G, which we can then tie back to enthalpy and entropy. Now, to calculate free energy at equilibrium, we can change that equation a little bit, because at equilibrium, delta G is equal to 0 and Q is equal to the equilibrium constant K. So our original equation was delta G is equal to delta G standard plus RT natural log of Q. Well, when we start to change it, delta G is 0 is equal to delta G standard plus RT. We're going to put the natural log of K here, because at equilibrium the reaction quotient is equal to the equilibrium constant. We're going to rearrange this so that we get delta G standard on a side of the equation by itself. So we're going to subtract this entire term and move it to the other side of the equation. So we get delta G standard is equal to negative RT times the natural log of K. So this top equation is for when we're not at equilibrium and not at standard conditions. Usually one of these two values has to be given to you then. And this bottom one is for when a system is at equilibrium, because at equilibrium delta G is 0, so we can solve for delta G standard using the rest of this equation. So since these equations are pretty different, it's important to remember that delta G and delta G standard for a reaction can have significantly different values. Okay, your question for this section. Consider the above reaction. Calculate the free energy change, delta G, at 25 degrees Celsius when 5 atmospheres of carbon monoxide and 3 atmospheres of hydrogen are converted to liquid methanol.